Guys, welcome to the channel that enables you to learn at your own time, pace, and place. If this channel is helping you, just hit the subscribe button to confirm. Enjoy. Hi guys, welcome to our video on electronics 1, and in this video we are going to look at two optoelectronic devices, the light emitting diode and the optocoupler. As usual, Motion Malfish, my name. I hope you are going to enjoy this one because it's not a new thing. You know light emitting diodes on our televisions, Wi-Fi's, smartphones, computers, those which emit light when they are turned on. Let's go. As usual, we start with objectives. This is what you should be able to do by the end of this video or lecture video presentation. You must be able to identify the light emitting diode as well as the optocoupler using their schematic symbols. Must be able, number 2, to describe the general construction of the light emitting diode as well as the optocoupler. 3, with the aid of circuit diagrams, you must be able to describe the operation of the light emitting diode as well as the operation of the optocoupler. Then, obviously, for each aspect in life, you must be able to state advantages and disadvantages of the two optoelectronic devices. Then, last but not least, of course, we all do this because we want to make use of the optoelectronic devices. So we must be able to describe the general applications of light emitting diodes as well as optocouplers in our everyday lives. This is very, very simple. No mathematics involved. We will start with the light emitting diode, in short, LED. LED. Please take note, I'm very disappointed with some of you. They cannot even give a symbol of a light emitting diode. I don't know. Guys, you must know schematic symbols of semiconductor or electronic devices. So a light emitting diode is a light emitter. It is an optical diode which emits light when it is forward biased. That is a very important point. Why? Because you must, when you are drawing a circuit, you must make sure that it is forward biased for it to be able to emit light or to operate. Then the construction of the light emitting diode is simply the same as that of a PN junction diode. It is operated in the biased region and so never in the reverse biased region. And most of them, they emit green. I think you are conversant with such light emitting diodes, yellow, orange, blue, to remember just a few. Please take note that we also have some light emitting diodes that emit infrared light, which is not visible to our eyes. Take note, it's an important point. Light emitting diode symbol and biasing. This is the symbol of a light emitting diode. It is also correct to leave this. This represents the housing or the casing, the glass casing which enables you to see the light being emitted by the diode. As you can see, this is important. Actually, this differentiates it from a rectifier diode or from an ordinary PN junction diode. This is showing that this PN junction diode emits light, hence it is called a light emitting diode. As usual, this is the anode and this is the cathode. If you are going to forward bias this diode as is required for a light emitting diode, you must make sure that the positive of the applied voltage is connected to the p-type material and the n-type material is connected to the negative. So this is the way how the light emitting diode is connected. So if you are asked to describe and explain the operation of a light emitting diode, make sure you forward bias it. These are showing that it is emitting light, hence the name light emitting diode. As usual, there is a barrier potential when the two are brought together, and the middle one is the junction. So our conventional current flow is moving in this way. How is light produced? Light is produced when recombination of an electron and a hole occurs. You remember recombination. For example, if you break up with your loved one and you reconcile, in electronics we call that recombination, because each would have gone his or her way. Then you decide to go back for one reason or another. Let's go through our literature. We are saying it is forward biased, and when forward biased, we are going to have majority charge carriers crossing the depletion layer. And when they cross, we are going to have recombination. Obvious, this we know. And we are saying free electrons are found in the conduction band and valence electrons are found in the valence band. And when an electron return that would have escaped from the valence band, when they return back, that's where we are going to have some photons of light being emitted. So recombination results in light being emitted. So we are saying when a free electron recombines with holes, this means that it would have fallen from the conduction band to the valence band. So you can simply say in analogy terms, when you guys break up and reconcile, the one who initiates that must fall from the conduction band to the valence band, and I hope light in your case is not going to be emitted. And its energy level falls from a higher to a lower value. And the energy corresponding to the difference between the higher level and lower level, we know is the energy gap, and it is released. You remember when an electron escapes from the valence band to the conduction band, it would have gained energy greater than the energy gap, but this time that energy must be released, and it is going to be released as light as well as heat. The LED, of course, it is made up of some special material which releases this energy as photons. Photons simply means light particles, and this results in the emission of light energy, and we call this process electroluminescence. Electroluminescence. And diodes which do that are called light emitting diodes. More on electroluminescence, and we are saying from our diagram, this is the conduction band, this is the valence band, and as I said, these are the two most important bands. The other bands, because they are attracted to the nucleus of the atom, they are not very important because their electrons will not escape, will not become free. So we are saying electrons must acquire energy greater than Eg, or the forbidden gap, for them to escape. But for them to fall from the conduction band to the valence band, or for recombination, they must release that acquired energy. And when they release that energy, we are going to have some photons of light being created. And so we are saying emitted energy is in the form of light. So this wall simply means that electron had escaped from the valence band to the conduction band, hence its charge is negative. Electron recombines with wall traveling from the conduction band to the valence band. I think this is very, very clear. And we are saying energy released in the form of light depends on the energy gap. That's very true. And this determines the wavelength. Wavelength, remember its symbol is lambda, and how do you calculate it? That's the speed of light, c divided by f. The wavelength of a particular signal determines the color of the light. I think you remember the issue of the sky being blue. It results from the blue color being emitted. And this also determines whether the light is visible or not, because we cannot see the signal from our remote controllers, which we use to control our television set by. They emit a certain wavelength of light. But what is the most important thing is to must be able to draw this diagram and to show the conduction band, valence band, the forbidden gap, electron being negatively charged, and but in the conduction band, and then a hole in the valence band. So this is going to escape from there and occupy a hole, and in that process it is going to emit. We are all aware of the addition of impurities, and we call it doping. And we are saying it is doping that controls the wavelength and also the color of the light, which means for us to have a blue LED, green LED, red LED, it is because of the doping process. And we are saying for silicon, we have got N 1.1 electron volts, which is the energy gap, the energy released when the electron escapes now from the conduction band to the valence band, as well as when it escapes from the valence band to the conduction band. And we are saying the wavelength of the emitted light corresponds to the, this simply means this is an electromagnetic spectrum. Never mind about it. What is important is to simply state that some normal LEDs produce light which cannot be seen, and we call that infrared light. Let's go through a bit of theory that is there. We are saying gallium, arsenic, and phosphorus. Remember, these are group 5 elements. So when you explain any type formation, make sure you must be able to, not you must be able to, indicate the group 5 elements that you would have doped with. Don't forget the symbols. We are saying silicon and germanium are not used for doping because they are sensitive to heat and are very poor in producing light. And the next point says the color of emitted light is decided by its wavelength. This is okay. This is a term which is mostly encountered in telecommunication. Never mind. Then the wavelength of emitted light depends on the value of the forbidden gap, because the value of the forbidden gap determines the energy or the amount of light released. Then forbidden gap value depends on the material used. Hence, the color of the emitted light depends on the material used. I think this is a self-explanatory slide. Light emitting diode construction. This is showing the construction of a light emitting diode. And as you can see, we've got 3 layers. The p-type on top, the active region between, and then we've got the n-type beneath. This 1, 2, 3 as indicated. This is an insulator. It's simply an insulator, and it has got a special name, and it's called a substrate. And we are saying these are holes in the p-type and these are electrons in the n-type. And we are saying when recombination occurs, that's when light is going to be emitted in all directions, and it is emitted in the active region. So we are saying we have got 3 semiconductor layers, 1, 2, 3. And we are saying the active region exists between the P and N regions as shown. And we are saying light emerges from the active region in all the directions when electron hole pairs recombine. And when forward biased, holes from p-type and electrons from n-type are driven into the active region. Mind you, we said n light emitting diode must be forward biased for it to emit light. So we are saying when it is forward biased, we are going to have electrons and holes being driven into the active region. And if recombination occurs, it means that light is going to be emitted. Self-explanatory. Must be able to draw and to explain better than I've done. Light emitting diode forward biasing is alluded to earlier, the light emitting diode must be forward biased for it to emit light. So the positive terminal of the applied voltage is connected to the anode. You know the anode is positive, while the negative terminal of the battery is connected to the cathode as shown. And VD shows the voltage that is going to drop across the light emitting diode. And we are seeing light being emitted when forward biased. It means that when reverse biased, there is no emission of light. RS simply stands for this is a current limiting resistor, so that the light emitting diode is not destroyed by excessive current. The current that flows in this direction, we are calling it I is the symbol for current, hence IS, because why our supply is VS, standing for supply voltage. You can go through the literature on your own. And as I said, the outward arrow represents light emitted, and it is associated with an light emitting diode. This is the current limiting resistor, and we are saying IS is the forward current. And please take note that the more the forward current, the more the light intensity emitted. But if you increase it beyond a certain range, this thing is going to go. It is going to be destroyed. I want to summarize that slide in one sentence. And I'm saying that slide in a sentence is showing the connection of an LED in a circuit. This is our light emitting diode. You can see by the two arrows indicating or standing for the rays of light. And this is our current limiting resistor. It does not matter. It can be put before the resistor or after the resistor. This has no effect on its current limiting capacity. So what are we saying? We are saying insofar as this applied voltage is concerned, it is a positive voltage, hence the positive terminal forward biases the diode. The same applies to this. The positive terminal forward biases the diode. This is our anode. Anode is positive, so it is connected to the positive terminal of the battery. Hence, the depletion layer is going to disappear. Hence, this diode is going to behave as an closed switch. Hence, it is going to allow current to flow. I'm done. Do light emitting diodes have advantages? Yes, they have. And the first one is they've got small size and they are light in weight. Hence, they are used in our smartphones and also in our digital devices, laptops, televisions, etc., etc. Then they are available in different spectral colors. They can be red, they can be orange, they can be green, so you choose. They have longer life as compared to lamps. They last longer. Light emitted is proportional to the amount of current flowing through it. Hence, we can control brightness by also controlling the amount of current flowing through it. Then it is very easy to interface with other electronic components or electrical components. Then it takes less than 1 microsecond to turn on or off, which means that they operate at very high speed. If you turn on your television, the LED light comes on there and then. So those are the advantages. Let's go to disadvantages in the next slide. As you can see, disadvantages are outnumbered by the advantages, hence their use. Can be damaged by overcurrent easily, very, very easily, and we have demonstrated that in our labs. Then the luminous efficiency is low for LEDs, that's the output. It is low for light emitting diodes. They need power for their operation. Without power, they don't turn on. Then they are affected by changes in the output power. Those are the disadvantages of light emitting diodes. The applications of LEDs are not new to us because, guys, we've got iPhones, we've got televisions, we've got smartphones, we've got laptops, we've got desktops. The list is endless. So we are now going to look at the light emitting diode applications. One, they are used as optical couplers in optical devices, for example, in optical transmitters. They are used as on-off indicator in our televisions, in our laptops. If you switch on the switch and the light does not come up, then you know it's either the device has got a problem or there is no power. Then in infrared remote controllers, when we are remotely turning on or off or controlling the brightness of our hi-fis or televisions, then they are used in all kinds of visual displays in our calculators, on our cell phones, to mention but a few. They are also used as alphanumeric displays, even in shops, on tills. You can add some more. The last optoelectronic device that we are going to look at is made up of the light emitter and light detector, and it's called an optical coupler or an optocoupler. It consists of two separate light emitter and light detector in one housing, and it can also be used to provide an isolation between the two, between a light source and a light detector. Please take note that its other name is opto-isolator. So a light emitter that normally is enclosed in the same housing as a light detector is a light emitting diode. And the other light detector, it can be a photodiode or a phototransistor. So we are now rounding up on optoelectronic devices. Let's go. This is a schematic diagram of an optocoupler, and we are saying this is a light emitter. This is a light emitter. It is emitting light. This is a light detector. It is going to detect incident light. This represents the housing. They are in one housing. This one is a picture of an optical coupler. So we are saying when current flows through this light emitting diode, or when it is forward biased, it is going to emit light, and this emitted light is going to be incident on the photodiode. When this photodiode senses light, its conductivity is going to improve. Hence, it is going to allow current to flow through it. You are going to see in one of the slides ahead a more detailed circuit joining the two, showing how they can be connected together to achieve a common goal. So we are saying there is no connection between this and this except through the incident light. And we are saying they are mostly used in optical fiber communication. This is an optocoupler, and it contains a light emitting diode as well as a phototransistor. This is a phototransistor, it's not a photodiode. Photo means light. And we are saying these are external components that are connected to the optocoupler. And what is happening, this represents a switch. This is a resistor, 150 ohm. This is also a resistor, 4.7 kilo ohms. This is a power. This is an applied voltage, 5 volts, and at the load we've got a positive voltage of 18 volts. So we are saying this is our input, this is our output. So this is the way how this thing operates, guys. When you turn on the switch, our current is going to flow, and as you can see, this light emitting diode is forward biased, so it is going to conduct and produce light due to recombination. When it produces light, the current is going to flow to 0 volts through this 150 ohm R1. So when this diode conducts, it is going to forward bias the base emitter junction of this transistor, and it is going to conduct. When it conducts, collector current is going to flow from the supply voltage through this. Then we've got a collector current plus base current is going to make the emitter current. So we are going to have an output voltage across R2. That's basically the way how the light emitter is controlling the light detector. That is a schematic diagram of an optocoupler, and as you can see, this is the housing. These are the legs of the, as you saw on that picture. It had 3 legs on one side and 6 legs in all. 1, 2, 3, 4, 5, 6. This is how the pins or the legs of an integrated circuit are numbered. You go down and then you go up. As you can see, IR stands for infrared, which means you cannot see this light. So it's an infrared diode, which means it is a light emitting diode, and it is emitting this light which is not seen, and it's called an infrared beam. This is the same as the light that comes from your remote control to your hi-fi or to your television. Then this is what we call a phototransistor. It's a phototransistor. The base is not connected anyway. Actually, it is biased by the infrared beam. As you can see, it is directed towards the base of this phototransistor. That's an explanation for the previous slide. I've mentioned the phototransistor, I've mentioned the infrared light emitting diode. Then you can see that the base connection of the transistor is open, which means it is unconnected. And we are saying for maximum sensitivity to the light emitting diode's light energy, or it's connected to ground via a suitable high value resistor, we want to reduce its response to noise, which means the response of the light. When the current flowing through the light emitting diode is interrupted, it means that the light is cut off, hence the transistor goes off. In other words, it stops conducting. And this phototransistor, and according to one of our previous slides, it can be used to switch current in the output circuit. Then this statement, we have got some types of optocouplers, and let's wait for the next slide to see them. Those are the types of optical couplers. As you can see, this one is a phototransistor. This one is a Darlington pair. It's a Darlington pair. As you can see, the two transistors are connected one after the other, with the emitter of the first one being connected to the base of the other is what we call the Darlington pair. Then we know that one. The other type of optical coupler, whereby we've got a silicon controlled rectifier and the light emitting diode. Then we have got the phototriac. So those are power devices. We'll do them when we do power electronics. So those, the important thing is you must be able to identify that it is an optocoupler, full stop. Go through on your own the optocoupler applications. There's nothing difficult. We said they are also known as opto isolators and can be used on their own or to switch a range of other electronic devices, as we saw in one of our previous slides. Some common applications include they can be used as microprocessor or microcontroller input and output switching, DC or AC power control, in personal computer communications, with signal isolation, power supply regulation. Yes, in switched mode power supply, they are used regularly or so often. Then I think that is it. Very soon we'll be electronics gurus because we are moving. This was our 12th video of presentation, and it was on optoelectronic devices. We looked at the solar cell, photocell, photodiode, light emitting diodes, the optocoupler, and we generally classified them as light detectors, light emitters, and a combination of the two. The next video, guys, is going to be interesting, and it will be on Zener diodes next week. So until then, guys, take care of yourself, and at your own pace, time and place, watch these videos on your favorite channel and enjoy them. Until then,